Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 10th, 2025, and we're diving into a fascinating piece of research. This ICLR conference paper, titled LARP, Tokenizing Videos with a Learned Autoregressive Generative Prior, was published on January 22nd, 2025, so just over 3.5 months ago. This paper introduces a novel video tokenizer called LARP, designed for autoregressive, or AR, generative models. These are AI models that create content, like video, step by step, where each new part depends on what came before. LARP aims to improve how videos are turned into these discrete symbols, or tokens, by looking at the entire video content holistically, rather than just small patches. It even uses a special helper model during its training to learn an optimal sequence for these tokens, making them better for video generation. Alright, so this figure really helps visualize what's going on. Part A shows the LARP framework, a two-stage setup where the tokenizer first learns with that autoregressive prior model. Then, Part B clearly shows this autoregressive prior model boosts video quality across different token numbers, measured by the generation Fréchet video distance, or GFVD, where lower scores mean better videos. Part C then compares models, showing LARP has a much smaller gap between its reconstruction Fréchet video distance, RFVD, and its generation Fréchet video distance. This smaller gap shows its tokens are well optimized for generation. Okay, this next figure 2, gives us a great side-by-side. On the left, in Part A, we see a typical patchwise video tokenizer, the old way, where video is just chopped into small local pieces. But on the right, in Part B, is the LARP tokenizer. It uses what they call holistic queries. These are special requests that look at the whole video content. Then a process called stochastic vector quantization, or SVQ, turns this holistic information into discrete tokens. And crucially, this LARP tokenizer is trained with that autoregressive prior model we talked about, helping it learn the best token sequence for generating new video. So after seeing how LARP is designed, this table, Table 1, really quantifies its success. It lays out a comparison of video generation results across various models. We see details like the number of parameters, which indicates model complexity, and those crucial Fréchet video distance scores, where lower means better video. Notice, LARP along achieves a reconstruction Fréchet video distance around 20, and then generation Fréchet video distance scores of just 5.1 on K600 and a state-of-the-art 57 on UCF 101. These results, particularly on UCF 101, outperform the other methods shown, really underscoring LARP's effectiveness. Building on those impressive results, this next table, Table 2, presents an ablation study. An ablation study, well, it's where researchers carefully remove or change parts of their model to see how each component contributes. They're looking at different configurations based on their LARP-B model. We see metrics like peak signal-to-noise ratio, or PSNR, a measure where higher scores mean better visual quality, and learned perceptual image patch similarity, or LPIPS, where lower scores are better. The most striking result is when the autoregressive prior model is removed. The generation Fréchet video distance jumps from 107 to 190, showing a big drop in generation quality, even though the reconstruction Fréchet video distance actually improves a bit. This really highlights how crucial that autoregressive prior model is for generating good videos. Alright, so after seeing those numbers, Figure 5 gives us a visual treat. We're looking at class-conditional video generation results on the UCF 101 dataset. This means the model was asked to generate videos belonging to specific categories, and we see examples like typing, people dancing, and someone playing the cello. These visual results really bring to life those state-of-the-art Fréchet video distance scores we saw earlier, showcasing the impressive quality LARP achieves. Following those impressive video examples, Figure 11 digs deeper into how these LARP tokens actually work. We see several video sequences, and below each, a heat map. These heat maps, well, they're visual representations that highlight the areas in the video showing the biggest errors in reconstruction when just a single LARP token is modified. What's fascinating is that changing one token doesn't just affect a tiny, isolated spot. Instead, the heat maps show that a single token can influence large, meaningful areas across the entire video. This really demonstrates that LARP tokens are content adaptive and influence global video structures semantically. So seeing how those LARP tokens capture such broad, semantic information really ties everything together. In essence, this work shows that by using a holistic tokenization approach, where tokens aren't tied to specific patches, and by co-training with that clever autoregressive prior model, LARP achieves truly impressive, state-of-the-art video generation. It's a big step forward for making autoregressive models work better with video. Well, that's all for this AI Research Roundup. Thanks for tuning in.